This is problem 12-102. Here you have a cantilever beam. It's being supported at a reaction point B, has a load P. From that I drew a free body diagram. Now this problem is a little unique in that you can't just make the assumption you can take the moment at A, set it equal to 0, and solve for B, because you always, when you have a cantilever beam, you're always going to have a moment. So that's why the free body diagram is going to look like this here, where you have a moment at A. If you sum the forces in Y, then you can say that FAY going up minus P plus FBY going up equals 0. But again, you cannot solve that. You can write this as FAY minus P plus BY is equal to 0, and you could solve for AY in terms of P and FBY. You could do that. What I did was went and took a moment at A, and I would get the P times L over 2, and made that negative because it's going back this way, plus FBY or BY, get rid of that, times L plus MA is equal to 0. I solve for MA here, and MA would just be PL over 2 minus BY over L. Okay, what you want to do then is just basically you're going to shorten the beam. And what I mean is you're going to create the beam just so it's like this, and you're going to let this point now be a value of x, which I did here. And again, you're going to write an equation for the moment of x. And when I do, I'll get the BY times some x value. I made that positive going up. And then the distance from here to here would be x minus L over 2, that's where I got this, minus P going down. So that's my moment equation. From that, go back to EI times the second derivative of your deflection over dx squared is equal to mx. Substitute this back into the equation. Move the dx squared up, and now you're going to integrate. When you integrate on this side, you'll just get EI dV, which is basically your angle of deflection at any point. And here, just x squared divided by 2. You treat this all as u, so you're going to do x minus L over 2 squared times du. Now du here is going to be 1. And make sure you divide by the 2, and then you add on the constant C1. If you integrate it again, you'll go ahead and get your deflection equation, which is EIV, and that becomes 3 divided by 3 gives you the 6. This becomes 3 divided by 3 gives you the 6, plus C1x plus C2. At this point, do your boundary conditions. So when x is equal to 0, so let's talk about what that means when x equals 0. When x equals 0, you're down to this very far end of the beam. The only thing that's going to be there is you cannot have any deflection, but your dV over dL is not going to equal to 0. Because that beam, if you think about it, let's get it in red, this beam is going to kind of deflect kind of like this, is exaggerating back up over here. And this would, now here, dV over dL will be 0. Your deflection will be 0, and your angle will be 0. Here, it's just deflection equal to 0. So let's go back to my boundary condition. So I wrote when x equals 0, no deflection, v is equal to 0. So from that point, if I put in 0 here, x is 0 everywhere, I can find that C2 is 0. So do that in red, so that's critical there. And then I said when x is equal to 0, I also get no deflection, which I wrote this, and I ended up getting just an equation with L in it. And that's basically one I'm going to work with. I just simplified as much as I possibly could. I ended up getting this equation here. Now, as noted, I said earlier that we know that dV over dL is equal to 0 when x is equal to 0. I'm sorry, when x is equal to L. So we do know that. So I said let's try to set this up. I set that up as my deflection equation here, and I set that up as my right here. I'll show you both of them. This is my deflection equation equals 0, and this is, excuse me, sorry. Yeah, that's my angle set to 0 when x is equal to L, and I also set one that my deflection is going to be 0 when x is equal to L. So I got two equations here. What I'm going to recommend, you have two equations, and you also have two unknowns. You don't know BYL, and you don't know C1. So what you can do, and what I did was here, I multiplied everything in this equation by L, which gives me 0 still on this side here. That gave me L cubed, that gave me L squared, and that gave me L here. Now I have two equations, two unknowns. I'm going to add the two together. What I did is I multiplied this one by upper one by negative. I'm going to add it to this one, which means I'm going to lose my C1 L's here. Now, to make things a lot easier, my denominator is 6, so I'll multiply by 3 over 3 here, 3 over 3 here. Here my denominator is 48, so 6 and 6 here. Add the two equations together. And as stated, I lost my C1s, and I get 1 minus 1/3 BYL cubed plus 5 PL cubed over 48. Move this to the other side. Here I'll get my negatives here, so my negatives are going to cancel out here. My L cubes will cancel out here and here. And then multiply everything by 3. That's going to give me 15 over 48, which is going to reduce to solving BY is going to equal to 5/16 P. So now, since I know that, all I have to do is put it into I put it into this equation here for BY, and I solve for L, or solve for C1. Well, let's do that, because I don't think this is right. This came from the solution manual, so let's just move this on down here. The 5/16, I agree with that. Alright, so let's move that down. Oh, excuse me just a second here. Let's take this equation here. Let's grab it. We'll put it right in here. Okay, so let's take this out here. We'll substitute back in, which we said we knew what BY was. And we said we knew it was, do it black, 5/16 P. Alright, so let's do this. Get common denominators here. That's going to give me 5 over 16 P. And make 32 here, because we got the 2 down there. L squared. Now we'll make this into, we need 32, so minus 4. So when we do that, that's going to give me PL squared over 32 plus C1 is equal to 0. So C1 is going to equal to PL, negative PL squared over 32. So that's what I wondered. I was wondering about that. There's a mistake in the solution manual. This should not be the cube power, this would be the second power. So let's take that out there. Alright, that makes a lot more sense. Okay, so once you have that, now you know BY, now you know C1. Now you can find AY by going back to this equation right here. Put in BY, we know P, and solve for AY there. That's how you do that one, and you should get 11/16 over P. And then to get your moment, you can go back to your moment equation at A right here and plug everything in, and you'll get the values. So anyway, there's a few typos there in the solution manual, so be careful there. But that's how you solve problem 12-102.